Let's look at some examples similar to the examples on the third and fourth page of the lab that you need to work out. Here we're given a velocity graph for a different glider experiment, and they want us to complete the acceleration graph. And so you should know that if I want acceleration from velocity, we have these three relationships, x, v, and a, all as a function of time. And I'm starting at velocity, and they want me to go to acceleration, so I know that is slope. And so the slope of this graph, we have a point here at 4 and 40, and why not pick 0 and 0? And so the slope, which is the acceleration, is 40 over 4, or 10 centimeter per dot squared, or centimeter per dot per dot. And so that I can draw a horizontal line. On the lab it says use a straight edge. I already did the lab with a straight edge, so I can just draw it in. You use a straight edge. Then the question is, what is the change in position of the glider between 0 dots and 4 dots? And so we have a velocity graph, and we want position, and so I'm going up. I want area, and so that's the area of this whole triangle. And so the change in position is the area, which is 1/2 the base. The base is 4 dots times the height, 40 centimeter per dot, and so I get 80 centimeters. Let's clear the screen to do the last question here. What is the change in position of the glider between t=1 and t=3? And so it is the area under the curve, or the area between the curve and the x-axis, and that is a trapezoid. If you like, you could break it up into a rectangle and a triangle, but let's do a trapezoid. And the area of a trapezoid is the base times the average height of a trapezoid. And so the average height would be 1/2 30 plus 10, and then the base, be careful here, the base is only 2. And the units here, this is centimeters per dot, and this is in dots. So our answer still comes out to centimeters, and so we get 30 plus 10 is 40, divided by 2 is 20, times 2, 40 centimeters. Another way to do it is to figure out the average velocity times the time. The average velocity is the distance over the time, and so the distance, which is what we want here, is the average velocity times the time. There's another equation for average velocity. It is the initial velocity plus the final over 2. And so in this problem, at t=1, that's the initial velocity for this problem is 10, and the final velocity is 30 over 2, and so the average is 20 centimeters per dot. And so 20 centimeters per dot times the time. This is really the change in time, so you have to be careful. Going from 1 to 3, change in time is 2 dots, and so I also get 40 centimeters. So either way is okay, but you do have to know it is the area. Let's take a look at the next example, similar to a problem you're asked to do in the lab. Here we're given an acceleration graph, and they want us to produce a velocity graph. And so if we think of this hierarchy of graphs, position, velocity, acceleration, all versus time. If we're starting at acceleration and want to go to velocity, we're going up. That is the area. And so let's just get the area all the way out to 4 dots here. And so we have the area of a rectangle. And so that is height 5 centimeter per dot squared times the width, 4 dots. And that gives me 20 centimeter per dot. And so that's the point there. And if you wanted to get another point, you could do that. You could get the area between 0 and 2. And so the width is 2, the height is 5, and so you're going to get 10. But it is constant slope for the velocity. And so we really only need this point, and we have to assume the initial velocity is 0. Do that on the lab as well. And you should use a straight edge. I'm just going to sketch it here. If it's a straight line going up, it should intersect here at 4 and 20. Let's take a look at the next one. Here we're starting with distance, and they want us to go to velocity. And once again, you should be able to do this in your sleep. If you're looking for an idea for a good tattoo, having this tattooed would be a good idea. Going down a slope, going up is area. And so here we're starting at distance, going to velocity, so we want the slope. And so the slope of this line, let's pick 80 and 4 and 0, 0. Always make sure it actually goes through 0, 0 before you use that. You get 80 minus 0 over 4 minus 0, and so that comes out to 20. And let's be careful here with the units. These were centimeters, these were dots, 20 centimeter per dot. Now what's unusual here, or at least what's different between this and the lab, is this slope is constant. So I know the velocity is always 20, at least in this time interval. And again, use a straight edge when you're doing the lab. And so we're asked, what is different about the setup of this air track? How is the velocity staying constant? In the lab, the air track was suspended up by a brick. And so and the glider increased its velocity as it went down. Here the velocity is staying the same. What is different? I will leave that up to you. Ask me a tutorial if you don't know. Let's take a look at the next one. And so this one is a little different here. Be careful. The units are miles per hour for the velocity and time in seconds. And so we're told a Lotus Esprit V8 turbo accelerates from rest to 60 miles per hour in 4 seconds. Assuming the acceleration is constant, what is the average velocity during this 4 seconds? Well, average velocity is change in distance over change in time, but we're not given the change in distance here. And so you could figure that out, but don't forget the other average velocity equation, the initial plus the final over 2. Now this only works for a constant acceleration. Otherwise it's just approximate. Whoops. Pretend you didn't see that. And so we're told it's constant acceleration, so this is good. The initial velocity, it started from rest, so that's 0. The final is 60 over 2, so that's 30 miles per hour. It's as simple as that. What time did it have this average velocity? Well, if we were to graph this, we know we start at 0, and at 4 seconds we are at 60. And we know this is a straight line because we have constant acceleration. The slope is constant. And so when did it have this average velocity of 30? I could have drawn a little bit better. You do better on the lab. 2 seconds. So halfway through. And we use this idea to construct our velocity graph for the airtrack glider. And so that's why I'm asking that. Well, if you have trouble with the conclusion, again, go back and take a look at the first part of this vodcast, and good luck with your lab. This is Mr. Burns signing off.